So this presentation is on estimating a population proportion based on a simple random sample. It's about the same material that's in the OLI textbook in Module 14 on pages 191 through 194, or in the class workbook, Module 14. It's either topic 1 or 2, depending on which edition of the workbook you're looking at. Now, so what do I mean by the population proportion? So I'm thinking about a yes-no survey kind of situation, and we want to estimate the proportion of the population that would say yes. I don't have access to the entire population. Maybe there's millions of them, so I'm going to use a simple random sample to try to represent the population. So we have this blue letter P for the population proportion, and then we have the green letter P with a little hat on it, which is just the proportion of your sample who say yes. And when I say sample, I mean maybe 100 people that you've selected randomly from the full population. And so we don't expect the sample proportion, the P hat, to be exactly the same as the P, but it might be close. And in fact, what we want to do is to calculate a margin of error so that most samples, and in this class we'll do either 95% or 90% or 99%. But let's say, just for the example, margin of error could be calculated so that 95% of all the possible samples would produce a sample proportion that differs from the true proportion by less than E. Now, how can we estimate the margin of error? The idea is to connect this to what we were doing before with estimating the mean of the distribution of a continuous random variable. Now this is a little bit different. You know, our yes-no variable is not continuous. Okay. But the idea is, if we knew that the P hat was normally distributed or approximately normally distributed, and if we knew that the mean of P hat was the same as the true population proportion, then we could use the same formula that we had previously. We could put it all back into the same context that was based on the central limit theorem. So, the next few slides are going to address how you go about creating that context. You see, we're going to need to know sigma, so I'm going to have to work out the standard deviation of this yes-no variable. And we're going to need some argument for why this P hat might be normally distributed. That'll be an application of the central limit theorem. And then once we've got those two things, once we have the known sigma and we have that the distribution of P hat is roughly normal, then we'll be able to write down our formula for margin of error. Okay, so we're going to start with a random variable x, and this is a binary random variable. It's either 0 if an individual's answer is no, or 1 if the individual's answer is yes. So X encodes the answer of a single randomly selected individual. And it has a probability distribution. So the index goes from 1 to 2 because they're two different values of x. The first value of x is 0 if the person says no. Second possible value of x is 1. So x1 equals 0 and x2 equals 1. And then we have the probabilities that go with each of these. P is the proportion or percentage of the population who would say yes. So P is the probability that a randomly selected individual will say yes if all the individuals were equally likely to be selected. So when you do your sampling, all the individuals have to be equally likely to be selected. Okay. And then if P is the proportion who say yes, 1 minus P is the proportion who say no. And now our first goal, now that we have this distribution, is going to be to work out the mean and standard deviation. So the mean of a discrete random variable is just the sum of the probabilities times the x values. We have two different x values, x1 and x2. So our mean is p1 x1 plus p2 x2. And we need to plug in the values of those. So x1 is 0, and p1 is 1 minus p, and x2 is 1, and p2 is just p. So when you put those numbers into the formula, you get 1 minus p times 0. Well, that just goes away. Plus p times 1. Well, that's just p. So the mean of x is p. The population proportion, which we don't know. Okay. And then for the standard deviation, you do the same substitutions. And the expression is a little bit messy. I mean, I replaced the P1 with the 1 minus P, and I replaced the P2 with the P, and I'm replacing the mu. We worked out in the previous step that mu is P. So there are all these replacements, and it's a mess underneath the square root, but you multiply it all out with FOIL and the distributive property, and you combine like terms, and you simplify it down, and the final result isn't so complicated. It's just P times 1 minus P. Okay. So, now that we know the distribution of x, I want to do the distribution of the sample mean of x. And we're going to use the central limit theorem to approximate that. So from the previous slide, we have the mean of x is p, and the standard deviation of x is the square root. Okay, and from the central limit theorem, we have that the mean of the sample means is the same as the mean of x. And the standard deviation of the sample means is the standard deviation of x divided by the square root of n. So we're going to plug that in. The mean of x bar n is the same as the mean of x, and that's the same as p. Also, the standard deviation of x bar n is this original standard deviation of x divided by square root of n, but we know the standard deviation of x from the previous slide. So we got all the pieces. So the sample mean of x is normal if n is big, and it has this mean and standard deviation. Now, it's easy to lose track of what the symbols mean. So what is the meaning of this x bar n? You take a sample with n different people in it. You get the x value for each person. It's 1 if they said yes, 0 if they said no. So you get all those x's from the people in your sample. You add them up and divide by how many people there were. X bar n, it's the average answer. Now think about that. You're adding up all these x's. It's a bunch of 1s for the people who said yes and 0s for the people who said no. So when you add it all up, you've got how many people said yes. And when you divide by n, that's the number of people in your survey, just the ones you asked in your sample. Okay, you're dividing by how many people did you ask. So you got how many people said yes divided by how many people did you ask. That's the sample proportion. The x bar n is the same thing as the p hat. So the sample proportion is x bar n. So the mean of the sample proportion is p. The standard deviation of the sample proportion is this big square root. And p hat's normally distributed. So it looks like we're good to go. We can just use our formula for the margin of error for the sample mean, because p hat is a sample mean. I mean, we're so close to finished. But the trouble is, we don't know p. That's the whole point. P is the population proportion. We don't have access to the entire population. The only reason why we're taking the survey in the first place is because we don't know p and we would like to find out. So we're kind of stuck. We got our formula for the margin of error all set, but we don't know p. Well, so the standard practice is to replace the p with the p hat. And this is justified. Well, there are arguments that it's an okay thing to do when n times p is more than about 5 and n times 1 minus p is more than about 5. And there's proof that, well, it just gets better the bigger that n is. So when we write down our formula for sigma, that's all of this big square root, and it really ought to have a p inside, but we're using the p hat as an approximation. And once we do that, then we've got all the numbers we need to find the margin of error. So here's an example. We take a survey to determine what percent of a population is left-handed. We get a simple random sample of 100 individuals, and 12% of them turn out to be left-handed. But that's probably not really the true population percentage. So we want to find a 95% confidence interval estimate for the true population mean, or for the true population proportion. So it's probably close to our 0.12, within plus or minus a margin of error E. So we're not going to be 95% confident that P is between 0.12 minus E and 0.12 plus E. Okay, well, our critical value of Z at the 95% confidence level is 1.96, because 95% of the time a normally distributed random variable will be between plus and minus 1.96 standard deviations away from the mean. And this big square root tells you how much is one standard deviation. So you just do the arithmetic and you get this 0.06. So about 12% of the population is left-handed, plus or minus 6%. So somewhere between 6% of the population and 18% of the population is left-handed. We're 95% confident that the truth is between 6% and 18%. What do I mean 95% confident? Well, I mean 95% of all possible samples of 100 people would not be off by more than 6%. Ours was one of those samples. 95% of them are this good. So in that sense, we think ours is probably this good. That's it.